Imagine a world where thought alone can move objects, communicate complex ideas, or even restore lost senses. This isn't science fiction, it's the rapidly evolving reality of brain-computer interfaces, or BCIs. We stand at the precipice of a technological revolution, one that promises to redefine human capability and interaction. BCIs are direct communication pathways between the brain and an external device. They bypass the body's natural motor and sensory pathways, creating a direct bridge between neural activity and technology. This field is not just about assistive devices, it's about augmenting human potential in ways previously unimaginable. At the heart of every BCI lies the incredible complexity of the human brain. Our brains generate electrical signals or neural impulses every time we think, move, or perceive. BCIs work by detecting and interpreting these intricate patterns of electrical activity. These signals can be captured in various ways. Non-invasive methods like electroencephalography or EEG measure brain waves from electrodes placed on the scalp. While convenient, they offer lower spatial resolution. Invasive BCIs, on the other hand, involve surgically implanting electrodes directly into the brain tissue. These provide much higher fidelity and precision in signal acquisition. They can capture the firing of individual neurons, offering a richer data stream for decoding. Once captured, these raw neural signals are processed through sophisticated algorithms. Machine learning plays a crucial role in identifying specific patterns associated with intended actions or thoughts. This decoded information is then translated into commands for external devices. The challenge lies in accurately distinguishing meaningful neural commands from background noise. Researchers are constantly refining these algorithms, making BCIs more robust and intuitive. This intricate dance between biology and computation is what makes BCIs so profoundly powerful. The impact of BCIs is already being felt in profound ways, particularly in the medical field. For individuals with severe paralysis or locked-in syndrome, BCIs are restoring a voice and agency. Patients can now communicate by simply thinking about letters or words, typing on virtual keyboards with their minds. Advanced prosthetic limbs are another remarkable achievement. Users can control robotic arms with their thoughts, performing complex movements with surprising dexterity. This allows for a level of independence and functionality previously unattainable for amputees. In neurorehabilitation, BCIs are showing immense promise. They can help stroke patients regain motor function by providing real-time feedback on their brain activity during attempted movements. This neurofeedback can help rewire neural pathways and accelerate recovery. Beyond direct control, BCIs are also being explored for pain management and mood regulation. By modulating specific brain regions, they offer non-pharmacological approaches to chronic conditions. These early successes are just a glimpse of the transformative potential. Despite their incredible promise, BCIs face significant technical and ethical hurdles. The long-term stability and biocompatibility of implanted devices remain a key challenge. Ensuring the safety and longevity of these interfaces is paramount for widespread adoption. Data security and privacy are also critical concerns. Brain data is incredibly personal and sensitive, raising questions about who owns this information and how it will be protected. Robust ethical frameworks are essential before widespread deployment. The potential for cognitive enhancement also sparks complex ethical debates. If BCIs can augment memory or processing speed, what are the implications for societal equity and human identity? We must carefully consider the boundaries of human augmentation. Accessibility and cost are practical considerations. Ensuring that these life-changing technologies are available to all who need them regardless of socioeconomic status is a vital goal. The journey from research to widespread clinical application is long and complex. Looking ahead, the future of brain-computer interfaces is nothing short of revolutionary. Imagine seamless integration with smart environments where your home responds to your thoughts, or perhaps direct neural interfaces for immersive virtual and augmented reality experiences. The potential for enhanced human cognition is particularly exciting. BCIs could one day allow for direct knowledge transfer, accelerated learning, or even shared consciousness. This opens up entirely new paradigms for education, collaboration, and human connection. In medicine, we could see BCIs used for early disease detection, personalized neurological treatments, and even repairing damaged brain tissue. The ability to directly interact with and understand the brain at this level promises unprecedented therapeutic avenues. The convergence of BCIs with artificial intelligence and advanced robotics will unlock capabilities we can barely conceive today. We are moving towards a future where the line between human and machine blurs, not in a dystopian sense, but in a symbiotic evolution. Brain-computer interfaces represent more than just a technological advancement. They are a profound exploration into the very essence of what it means to be human. They challenge our understanding of consciousness, identity, and our place in the technological landscape. For medical professionals, tech enthusiasts, and neuroscience students, this is a field ripe with opportunity. The challenges are immense, but the potential rewards are even greater. We are at the dawn of a new era where the power of thought is becoming an interface to the world. Join us in shaping this incredible future.